Hey, what's going on guys, and welcome to our 5th signal processing tutorial. It's just going to be a quick one today, but this is required background knowledge as we progress forward through some of the tutorial questions. Today's tutorial is going to be on Bode plots. Now, what are Bode plots? Bode plots describe how a signal is attenuated over a range of frequencies. Bode plots are typically drawn with decibels as the gain and a log omega scale as the frequency. Okay, so you might be wondering, what's this in the top right hand corner, and what are poles and zeros, and what do they have to do with our Bode plot? Well, a zero of a transfer function is simply a zero in the numerator of the transfer function, while a pole is a zero in the denominator of a transfer function. For instance, if we had the transfer function s plus 1 divided by s plus 4, we would have a pole at negative 4, and we would have a 0 at negative 1. Okay, so now you might be wondering, how do poles and zeros impact our Bode plot, and in turn, how do they impact how our signal is attenuated over a given range of frequencies? Well, a pole causes a negative 20 decibel per decade drop-off in magnitude, while a zero causes a 20 decibel per decade increase. In our Bode plot on the left here, we can see that there is a pole at 0.01, as past this point is a negative 20 decibel per decade drop-off. From 0.01 to 1 is a 2 decade increase, and we've dropped 40 decibels. Then, at 1, there is a 0, which adds 20 decibels per decade to the attenuation. Essentially, this cancels out our pole, which causes the flat section of our Bode plot. Lastly, there's an additional pole at 10, which causes another negative 20 decibel per decade drop-off. If we were to write our transfer function of this system, t of s, we would write, firstly, all of the zeros, which is s take 1, as there is only one zero at positive 1, divided by all of the poles, where we know there is a pole at 0.01, therefore s take 0.01, and there's also a pole at 10, therefore we have to have s minus 10. Okay, so this takes into account all of the poles and zeros that we can see on our Bode plot here. However, it doesn't take into account the fact that all of the frequencies below 0.01 radians per second have a magnitude gain of 40 decibels. How do we take care of this? Well, we can multiply our transfer function by a value at the front, say 40. However, this 40 is decibels, and this isn't. So we need to find out what value would give us 40 decibels. If you're not familiar with decibels, I'd suggest you look up some other videos first. Teaching that is probably outside of the scope here, so I'm just going to assume that you know it. If not, I'll give you a quick way to convert to and from decibels. Say we have a value of 40 decibels. We can find this by 20 log base 10 of x, where x is our value in non-decibels. So, from here, we can solve for x. We can divide through by 20, which gives log base 10 of x equals 40 divided by 20 is 2. Then we can use an inverse log to give us x equals 10 to the power of 2, therefore x equals 100. So for our case here, we'd have to multiply our transfer function by 100 at the front, which would give us the value of 40 decibels for any frequencies which are below 0.01 radians per second. Well, I know this one was real quick, guys. I just wanted to make sure you had a good understanding of what Bode plots were and how to derive the transfer function from them, or how to derive the Bode plot from the transfer function. As always, thanks for watching. If you had any problems at all, feel free to leave a comment down below and I'll get back to you. I'll see you guys in the next one.